Hi, in this example problem, I'm going to work through a number of examples of using Lenz's law. Lenz's law is a conceptual law that goes along with Faraday's law of electromagnetic induction, and it tells us the directions in which induced magnetic fields and induced currents are directed in when electromagnetic induction occurs. Before we get started, I want to show you one thing quickly here. So there's another way, an alternate way that's sometimes simpler to do right-hand rule number 2 when you're dealing with electromagnets that have loops. Examples of loops are as you see here in part A on right-hand rule number 2 below, right? There's a loop of wire, and with the right-hand rule number 2, if you go ahead and wrap your fingers around the wire with your thumb in the direction of the current, then your fingers point in the direction of the magnetic field. And in particular, we can see for the loop there on the left that the field is always pointed up, coming out from the bottom to the top. That means that this loop behaves like a magnet with a north pole on the top, a south pole on the bottom. Now, anytime you have a loop electromagnet, it could be a loop of wire like this, could be a coil of wire like a solenoid. There's another way to do this. Take your right hand and you switch the roles of things a little bit. Wrap your fingers in the direction of the current, and your thumb will naturally point in the direction of the North Pole. I want you to be careful with this alternate right-hand rule because it only works for loops, whereas the right-hand rule number 2 works for any current configuration for electromagnet. However, when you do have loops, which frequently we do, this alternate right-hand rule is a useful one because it can quickly tell you, if you know the current direction or the magnetic field direction, how they're related in a loop electromagnet. All right. Here's the first one we're going to look at. So we've got two loops in case A and B. It's broken in case B. And we have a permanent bar magnet that's falling from above with the North Pole coming down. Question is, what direction will an induced current be, clockwise or counterclockwise, or will there be none in the metallic ring there, or loop? Well, we can see that there's a North Pole that points down, right, from the magnet. But remember, magnets are like this, right? The field lines curl around, they come out of the north, they go back to the south, and then they continue to go back up on in the inside as well. But notice how it gets weaker further away, where there's more spread between the field lines. If you get closer to the pole, it's a stronger field, right? So as this thing falls down, basically the magnetic field points down, right? So in the middle of the coil, the field that goes through, it points down, but as the magnet gets closer, it's going to grow. It's going to get bigger, 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 right? You see that as the magnet comes down, it just gets bigger and bigger, bigger. And because of that, we have an increasing magnetic flux. So I'm going to go ahead and draw with a green arrow. We've got passing down here, we've got increasing magnetic flux, right? In other words, the change in magnetic flux is to increase in the downward direction, right? Because Lenz's law, which says nature opposes any change in magnetic flux, nature doesn't want it to grow, and it's growing down, so it's going to go ahead and create its own magnetic field. So I'm going to draw the magnetic field that it's induced here as going up. So there's B induced to oppose the change so that it doesn't grow down as much. And the current direction, if we use the right-hand rule number 2 or the alternate rule, we see that the current has got to be going in this direction and looking up from above. So if we're above here and we're looking down there, here's our eyeball, we're going to see that this is a counterclockwise current here. Your induced current, it is counterclockwise as viewed from above. So in A we got counterclockwise, and in part B, what are we going to have? Well, we also have a change in magnetic flux. Nature doesn't like it. It would like to produce an upward induced field to counteract it. However, because of this break here, we can't have any current flow. You will have charge pile up at the ends of that break because we still have this induced EMF, which is like a battery, but we won't get current flow, so we're not going to get a induced field that's strong. All right, let's look at another one. And so what I really want to point out is that this effect of having a changing magnetic flux, it is generating an EMF. Remember EMF, this thing. It's effectively the same as a voltage for a battery. And so that's why we're getting these induced currents. This EMF that's induced is just like a battery, and it creates currents. In fact, when we have a power generator, this is how it's done. And the way that our houses are powered, it's done by these power generators, right? So it's actually the induced EMF that we're using in our households. I want to show you that we can use this to charge a capacitor as well. So in this particular picture, we've got a magnetic field that points out of the paper. It says the magnetic field is decreasing in time. This is important. It's decreasing in time. Which direction is the magnetic flux? Let's use green to look at a magnetic flux. So the magnetic flux, because the B field is pointed up out of the page, this magnetic flux is out of page, but it's decreasing. So it points out, but it's getting smaller. And this is similar to some other cases we've seen. Because it's shrinking in the out-of-page direction, we're going to instead have an induced field that's going to point out. So I'm going to draw it in purple. And this induced field, it's not going to be super strong or last for a long time because the capacitor, like in the previous example, is kind of a break in the wire. However, we do know what direction the current would need to flow if we use the right-hand rule. If I point my thumb straight up with the alternative rule to produce this purple out-of-page B field, right? Here's my B induced. Then I need to have thumb straight up in the North Pole direction. My fingers, if I curl them around the wire loop, they're going to go in the counterclockwise direction. So we're going to have an induced current that looks like this. And so positive charges are going to pile up over here. Negative charges are going to pile up over here. And it'll continue until the, either the external field, the red dots, stop changing, then it'll immediately stop and neutralize the capacitor, or it'll continue to charge until it reaches the same EMF as produced by the changing magnetic flux. So in this case, I just want to show you that we can use an induced EMF just like a battery to charge a capacitor. And so these two things, this guy, whether you have a battery or an EMF, they act in the same way, essentially. You can't distinguish the actions of the two. Let's look at one more case here. We've got a picture here now. Let's just remember what the magnetic flux is equal to. Magnetic flux is equal to the magnetic field strength times the area times the orientation between the loop, the normal line, and the magnetic field vector. In this case, previously we just saw examples where B was changing, right? Here's a case where we have a constant B field everywhere. This thing stays the same, but the area, this thing is increasing. And let's see if we can figure out what direction is the induced EMF, induced magnetic field going to be. Well, right now the EMF, sorry, not the EMF, the magnetic flux, it's into the page, because we see that external field with X's is pointed into the page, right? And look at the area. As this thing moves in this direction, the area is growing. It's increasing, right? Therefore, the flux is into the page and it's increasing as more and more magnetic field flows through the loop. The reaction to that is to oppose the change. It doesn't want it to get big into the page, so we're going to go ahead and try to have magnetic flux point out of the page by generating your own magnetic field with a current in the wire. And the current in this case, as you can see, is going to go, it's going to go straight around the edge of the conducting wires to the light bulb, and it's going to make the light bulb shine. So we've got the B field, so B induced is out of page, and we notice that the effect of this induced magnetic field, right? It creates this current that goes in that direction. What's the current driven by? It's driven by the EMF that's induced, which acts like a battery, which powers that light bulb. However, as soon as you stop pushing along the bar on the conducting rails, once that stops, the magnetic flux will no longer be changing. Then nature has nothing to oppose anymore, and the light bulb will turn off. So in essence, the person pushing that aluminum block along the conducting rails is doing work. It actually takes effort to push it, and that work is causing the current to flow, which is causing the light bulb to light up. I realize for this one I forgot to put the direction of the electric field, but that's going to be easy enough. If I draw the electric field, say in blue, it's going to go from the positives to the negatives inside the plate region.